Hello everyone, and welcome back to another episode of the Evolutionary AI series. In today's episode, we are going to talk about genetic algorithms again, and we are going through a toy problem. If you like the video, subscribe to the channel and give a video a thumbs up. Alright, so let's start from the setting that we are trying to deal with in this particular video. So we are going to have a grid word with 4 columns and 3 rows. In this grid word, we have a cleaning robot that has to reach a charging station represented by the green square on top, avoiding a flight of stairs. So the robot has to move in this grid word one step at a time. This is a discrete environment. We have discrete time, discrete space, and the goal is to reach the charging station on top, avoiding falling down the stairs. Okay, to make the problem a little bit more interesting, we are going to use a stochastic transition model. What is a stochastic transition model? It's a model that tells the robot how it should move inside the environment. Okay, the robot doesn't have access to the transition model. The robot can just take a specific action. In the action here, we will have 4 of them. It can be up, down, left, and right. But every time that the robot takes an action, the transition model is going to apply a stochastic operator that in 80% of the time will make the robot move in the direction that the robot has taken, but in 20% of the time will make the robot shift in different directions. So let's assume that the robot wants to move up, like here, this representation. 80% of the time the robot will be able to move up, but in 20% of the time the robot will not move up. 10% of the cases will move right, 10% of the cases will move left. The same things will happen if the robot tries to go down. If the robot wants to go down, 80% of the time will go down, 20% of the time it will just go left or right. So for every action, we are going to have this specific stochastic transition model applied on top of it. All right. We're also going to have a reward matrix for every location of this grid word. So for most of the standard locations, the reward is going to be small and negative, minus 0.04. And for the terminal states, the green one, the reward would be +1. And for the red one, the reward would be -1. Now, as you remember from the previous video, we need here to define a fitness. We want a fitness score for the robot in this case, when it moves inside this grid word. We can use the reward to get a fitness in this case. So the reward that is named R here, we are not going to use the exponential here, so we are going to use the reward R at time step t. We are going to sum all the rewards obtained at every time step, and we are going to do it over multiple episodes. So M is the number of episodes, N is the number of time steps. Of course, we are going to assume a limit to the number of time steps, let's say 50. So the robot can move just 50 times inside the grid word, and depending from the policy that the robot is going to use, these 50 steps can be exhausted or not. The robot may go directly to the green charging station in just a few steps, and therefore we are not going to exhaust the 50 time steps available. But in other cases, if the robot goes in a loop or continue to bump against an obstacle, then this means that we are going probably likely to exhaust these 50 time steps. Another important thing to consider is that this gray square at the center is just an obstacle. So if the robot tries to move through the obstacle, nothing is going to happen. The robot will bump back to the original position. And the same thing happens for the contours of the grid word that are also made of walls. So if the robot tries from this location, try to go on the left, it will just bump against the wall. It will remain in the current position. Also in that case, the reward will be negative, minus 0.04. And only in the terminal states we will have a reward that is different from minus 0.04. Okay, now given this particular setup, with this particular grid word and this particular reward matrix and transition model, there is one specific optimal policy that is the best one for this particular word, and is the one that we want to find. So our goal in this environment will be to find the optimal policy. that is represented here. Okay, this is the optimal policy for this environment. What is a policy? You can imagine like in this particular word, it would be like a set of instructions. Given a specific location, let's say 1, 1, you're going to check into a lookup table what you have to do, and the lookup table is telling you to go up. So the robot will just have a lookup table, it will have access to this table, and the table will tell the robot what to do at a particular location in the grid world. Of course, there are no actions associated with the terminal states. Once the robot reaches the terminal states, the episode's finished, so there is no real action that the robot can take, and there is no real action that the robot can take in the, inside the obstacle, because the robot cannot pass through the obstacle. So our goal today with genetic algorithms will be to find the optimal policy. Once again, this is a toy problem, so we are assuming that we don't have access to this optimal policy, and this is what we want to find. We can make this problem arbitrarily more complex, we can increase the size of the word, we can change the reward matrix, we can change the transition model. So take this with a grain of salt, but it's just a very simple toy problem that we're going to use to understand how genetic algorithms work. In previous video, we also have been talking about genotype representation. We have chromosomes. Each chromosome is a sequence of integers, floating point, bits, or characters. So we need to, for every specific problem, we need to define a specific genotype representation. For the toy problem that we're trying to deal with today, we have to consider which one of these 4 representations will be the most appropriate here. So take 1 minute, maybe you can pause the video, take 1 minute to try to understand which one of them will be better suited to solve the problem. Here you can see what I will personally pick. The 2 solutions that we can use are the label representation using characters or the integer representation. So we have 4 discrete actions, that is up, right, down, left, and to each one of these actions we can associate a letter or an integer. So we have a discrete set of options, 4 in this case. Each one of these options, each one of these actions will be mapped to a specific label or to a specific integer. And this will represent our chromosome. So let's go down into details. What does it mean to create a chromosome from a policy? So the optimal policy, as I told you before, is this one for this specific environment. This is the policy that guarantees to find the charging station in the best way possible. Before starting, actually, I want to talk about this particular location. As you can see here, the robot is going up, and the one below, the robot is going left. So what's going on here? Why the robot doesn't go up, up, and then can finally reach the charging station? Well, what's happening is that, as I told you, there is a stochastic transition model. So if the robot goes up to this location, what can happen in this location, even if the robot wants to go up, in 10% of the cases it can fall down the flight of stairs, and this is not optimal. So this is why the robot in this particular location wants to move left. It wants to avoid the danger of falling down the flight of stairs due to the random stochastic model. Okay, so every action in this grid world will be mapped to a number if we want to use the integer representation, or it's going to be mapped to a letter if we are going to use the literal representation, the label representation. In this case, for each location of the grid world that we have access to, in this case 1, 3, so it would be column 1, row 3, the action of the optimal policy is move right, and this is what we get here, move right. So this will be mapped to a letter, will be mapped to a specific number. And we'll do the same for every possible location of the grid world, right? So every location of the grid world that we have access to, that are basically all the locations, but of course the obstacle and the 2 terminal locations, because there are no actions associated to them. Each one of these locations will be associated to an action, and then in our chromosomes will be associated to a number and a letter. All right. Now, if you go back to our previous videos, you will see that we start with an initial population that is typically randomly generated. So in our case, since we have 4 letters, we can randomly pick a letter and we can assign each one of these letters to a gene, to a specific location of the chromosome. We are going to have 100 individuals, each one represented with a specific chromosome. So each individual is a specific policy that can be executed inside an environment. So this will be the control policy of a given robot. You can imagine like if there are 100 different robots, each one of these 100 different cleaning robots is controlled by its own policy. Okay, so initially we randomly generate different solutions, different policies. Most of them will not make any sense. So you will have a robot bumping continuously against the wall or trying to pass through the obstacle. So most of these solutions probably don't make sense. However, a few of them maybe they will be slightly better than others, right? And this is where the magic of genetic algorithms will start. So this individual will perform better, will be selected, they will generate offsprings, and these offsprings now will be variation of these specific policies. So they will also, with high likelihood, do better, right? And so on and so on, right? So every generation we are going to select the best individuals, the elite, they are going to reproduce, they're going to generate offsprings, and then the policy is going to get better and better. Okay, once we have the initial population, what we can do, we can select every individual of this population. Let's assume that we are starting with individual number 3. Okay, individual number 3 has this particular chromosome. What we do first is we turn the chromosome into a policy. So we map each one of these gene location to an action. We can do it through our legend. So in our legend, we have 4 actions. Each one of these 4 actions is mapped to a specific letter. So the letter D is mapped to action left. As you can see, every time that we have letter D, we map to left. Letter C is mapped to down. So every time that we have a letter C, we map to down, and so on. So we can turn basically a chromosome into a policy. And then what we need to do, we need to execute this policy into the environment. And we're going to do this for M episodes. So why we need to execute this policy for M times, for M episodes? It's because, once again, we have a stochastic transition model. So it's true that the actions that we have in our lookup table are always the same, right? But even if the actions stay the same, this stochastic transition model will change this action with the probability that we have described above, right? So this action, go right, will be executed only 80% of the time. 20% of the time, it can happen that the action will be turned into go down or go up. So this is why we need M episodes, because the final reward that we are going to get for every episode could be slightly different due to this stochasticity. Now, once we have the M episodes, we can evaluate the fitness. So if you remember what we have said before, the fitness is going to be the following. It's simply going to be, in this case, the sum of all the rewards obtained at every time step for M episodes. So we're just summing, doing a big sum of all the rewards accumulated in all the lifetime of the agents, in this case, for all possible episodes. And this will be a single number, and this will be the fitness. Okay, now we repeat this process for all chromosomes that we have in our initial random population, right? So assuming we have 100 individuals, after we have completed this process for each one of them, we're going to get a fitness score for each one of the 100 individuals. As you can see here, the reward in this initial iteration is going to be negative. Why? Because, well, there is very high likelihood that this policy don't make any sense, right? So the robot will continue to bump against a wall, against an obstacle, accumulating at every time step a negative reward. Now, if you're going to sum these negative rewards over all time steps and over all episodes, you can see why we're going to get a negative number like the one that you see here, like minus 25, minus 51, and so on. So once we have obtained the fitness scores, we can now sort them. What does it mean, sort them? We're going to sort each individual in the population from best to worst. Individual number 32 in our case, is the one with the best fitness score, minus 3.1. Then individual number 15 has a fitness score of minus 9.5, and so on. So the last individual number 42, has a fitness score of minus 92.9. This is the worst score in the entire population of 100 individuals. Then we're going to perform selection. In the previous video, we have seen two types of selection mechanisms, truncated selection and roulette wheel selection. For simplicity, we can apply truncated selection. So we're going to take the top k individuals. So let's say we're going to get top k here, represented by the green color. So the green color here represents the individuals that we are going to select. Red colors are individuals that we are going to discard from the population. Now, on top of the green group of elite that we have selected, we're going to use mutation and crossover to generate offsprings. So we take the top k individuals, we apply the genetic operators of mutation and crossover, and this will give us a new population of 100 individuals. So let's assume that we take just the best top 5 individuals of the population. We can use the top 5 chromosomes to generate 100 chromosomes. And these chromosomes, of course, will be variation of the top 5 solutions that we have selected. And this K, of course, can change, depends on the problem. You may want to focus immediately on the best solutions on top. So you may take the top 5, top 10, or you may leave a little bit more room for variation. So you may take the top 20 or 30 and so on. But the important thing to understand here is that we repeat this in a loop. So now we get a new population, right? We get generation 1 with new 100 individuals, but these 100 individuals will be similar to the initial selected elite. Now, assume you are repeating this process for many generations. Let's say 100 generations, okay? So you have 100 individuals mutated over 100 generations. At the beginning, we have seen that most of the solutions are completely random, so probably the policies are not great. You will have all sorts of behaviors, robot bumping into walls, into obstacles, or going in a loop, and so on. But if you look at the chromosomes, at generation 100, and you sort them best to worst, what you're going to see is something interesting. So the chromosome at the top, the best, at generation 100, there is high likelihood there is going to be our optimal solution. For this simple toy problem, perhaps 100 generations are going to be enough. We will be able to find the optimal solution quite rapidly. So the top candidate here, with high likelihood for this problem, is going to be the optimal policy. Now you can also look at the position number 2, position number 3, and so on. And what you notice is that position number 2 is identical almost to the solution on top, to the optimal solution, but there is one variation, one mutation of the chromosome. Same thing for solution number 3. It is also very similar. There is only one location where the optimal solution on top and chromosome number 3 differ. So it's clear what's happening. It's we're going to select a subset of the population, and through the generations, this subset of the population is going to survive, and you will have offsprings that are related to each other, and they will be very similar to each other. But if you go down, if you go, let's say, to the individuals number 100 at the bottom of the list, you will see that probably the solution will be different than the optimal one. It will be probably a suboptimal solution that is still good to reach the charging station and to avoid the flight of stairs, but is not the optimal one. So there may be some tiny difference in actions taken. So of course, this is a toy problem. It's just a way to help you understand overall how genetic algorithms work. In the next video, we'll go a little bit deeper into details. We will also see some Python code, how we can implement this grid word, and how we can change the size of the grid word and make this problem arbitrarily more complex. Once again, thanks for watching, and I will see you to the next one.